In the early 1700s, sailors could usually find latitude by watching the sun or stars, but longitude was the problem that turned the ocean into a very large guessing game. A captain could be confident he was near home, write that confidence into a logbook, and still discover the coastline had quietly moved 60 miles in the wrong direction. In 1707, a Royal Navy fleet under Sir Cloudesley Shovel struck rocks near the Isles of Scilly, losing 4 ships and more than 2,000 men. The disaster was not caused by one simple mistake, but it made one fact impossible to ignore. At sea, not knowing east from west could become fatal.
So in 1714, Parliament offered rewards through the Longitude Act with up to £20,000 for a method accurate enough to guide a ship across the ocean. That was not prize money. That was please stop feeding expensive ships to rocks money, which is one of government's more understandable moods. The reward pulled in astronomers, mathematicians, instrument makers, inventors, dreamers, and the occasional person who believed the answer was magnets, sympathy, or confidence. One possible answer was the moon, because if you could measure its distance from stars and survive the calculations, the sky could tell you where you were. Another answer was time, because Earth turns 15 degrees every hour, so the difference between local noon and home time reveals longitude. Then John Harrison entered the story, not as a famous university astronomer, but as a carpenter and self-taught clockmaker from the north of England.
Harrison was not polished by academic society, but he had something more irritating to polite experts. He was right about gears. By the mid-1720s, his long-case clocks were already astonishing, keeping time to about a second in a month when many clocks were still negotiating with the weather. His idea was brutally simple. Carry the time at a reference place, compare it with the sun at sea, and let the clock turn confusion into coordinates. The math was elegant, but the engineering was rude, because a ship is basically a wet wooden argument with gravity. The hard part was building a timekeeper that could survive heat, cold, salt air, humidity, and rolling decks without throwing a tiny mechanical tantrum.
In London, Edmund Halley listened, then sent Harrison to the respected clockmaker George Graham, who became an important supporter. Harrison's first sea clock, later called H1, looked less like a pocket watch and more like a brass machine that had ambitions of becoming furniture. In May 1736, Harrison and H1 sailed to Lisbon aboard HMS Centurion, and the voyage out was rough enough to humble both man and machine. By the return journey, though, H1 began proving itself, and Harrison correctly warned that a headlined officer's thought was start point was actually the Lizard. That meant the ship was roughly 60 miles off course, which is the kind of correction sailors prefer before the rocks provide peer review.
The commissioners gave Harrison money to keep working, and he promised an improved version within 2 years, because apparently optimism was also spring-powered. Then Harrison did something that makes him either admirable or exhausting. He found flaws in his own solution before the sea did. H2 never sailed for the prize because Harrison decided its design had a weakness, and he refused to pretend a nearly right machine was good enough. H3 became a 19-year siege, packed with experiments, refinements, failures, and the sort of stubbornness normally found in locked doors and committee minutes. It sounds maddening, because it was, but H3 also gave Harrison crucial innovations, including ways to fight temperature changes and reduce friction. Then came H4, the device that changed the story by shrinking it. H4 looked less like a sea clock and more like an enormous silver pocket watch, neat enough to hold and accurate enough to embarrass a century.
Inside that silver case was decades of obsession. Jeweled parts, fast ticking, careful compensation, and a craftsman trying to make time ignore the weather. In 1761, Harrison's son William carried H4 on a voyage to Jamaica, where the watch performed with stunning accuracy after weeks at sea. At Jamaica, H4 was judged to be only about 5 seconds off, a result far inside the standard needed to solve the longitude problem. That should have been the triumphant scene where everyone applauded, paid the man, and admitted the carpenter had beaten the ocean.
Instead, the Board of Longitude became very interested in further proof, full disclosure, repeatability, and every other word that makes victory sit back down. To be fair, public money required a reproducible method, not a miracle locked inside one brilliant watch. To Harrison, it looked like the rules were moving every time he reached them, which is a familiar exercise in the history of paperwork. A second major trial, this time toward Barbados in 1764, again showed that H4 could meet the strictest demands. The argument dragged on anyway, because the longitude problem had two solutions fighting for authority: Harrison's timekeepers and the astronomer's lunar distance method.
Neville Maskelyne and the Nautical Almanac helped make lunar distances practical, while Harrison kept insisting that a working watch had already done the job. Harrison answered with petitions, explanations, demonstrations, and the exhausted fury of an old inventor who had spent a lifetime making brass tell the truth. Old, nearly blind, and deeply angry, Harrison eventually appealed beyond the board, and King George III took an interest in testing the watch himself. In 1773, Parliament awarded Harrison additional money, though not in the clean, satisfying way the original prize had seemed to promise. Harrison died in 1776, with the longitude problem effectively solved, but the paperwork still looking like it had survived out of spite.
Chronometers did not flood every ship overnight, because early marine timekeepers were expensive, delicate, and required skill to use. But over time, makers improved them, navigators trusted them, and a ship could carry accurate reference time into parts of the ocean that had once been mathematical fog. What changed was not just navigation, it was confidence, because a captain could know east and west with a precision that had once seemed impossible. A ship could now carry a tiny piece of Greenwich across the world, ticking calmly while storms, currents, and bad charts tried to lie. That is why Harrison changed the ocean. He did not make the sea smaller, safer, or kinder, but he made it harder for the sea to hide where you were. And that is John Harrison, the clockmaker who changed the ocean, so oddly human that his greatest voyage was not across water, but through 50 years of gears, doubt, and bureaucratic weather.